Today I'm going to talk about rehydration versus direct pitching of our yeast and what is the best or what is not. But first, I'll do this every week because we have new participants every week. Just to shortly discuss the guidelines of the webinar, how it works. The presentation will take around 40 minutes. Today it will be a bit shorter, I think, because a lot of information, as you will see, is it's very similar but you'll see. I will not explain now. There's always room for questions. You can leave them for after the webinar, but if you have an urgent question, you can always ask Alar via the chat. You can do that in English or in Estonian, it doesn't matter. Then Alar will contact me and ask me the question in English, because my Estonian is not that good, actually, to be honest. He can also give you direct access, so you can also enter the room with sound and your webcam if you want. But so far, most people just ask the question via the chat. So, as said, if you have an urgent question, just ask it immediately, but if you can save them for later, at the end, it's also fine. So we have a program, and today is only the second webinar in the cycle. The content will become more and more valuable and deep as we go, in the cycle. So today it's rehydration versus direct pitching, and next week I'll talk about the impact of temperature, pitching rate, and original gravity on the flavor profile of beer, and I will highlight both lager and ale yeast, and the others you can read. We do this every Thursday at 10 a.m. your time. For me, it's 1 hour earlier, actually. It's 9 here. I'm in Holland. So just a quick introduction on where we are. So Fermentis is part of the Le Saffre group. We are our headquarters is in Lille, or near Lille, actually, in the north of France. It's shown on the map. I will try to get my pointer. It's here. It's a very nice city, so if you ever have the opportunity to visit, please do. You guys are here in this beautiful country. So if you fly, it's about 2.5 hours or something. So Fermentis is a business unit of Le Saffre that mainly focuses on the world of fermented beverages, so beer, wine, cider, spirits, and potable alcohol. Today I will obviously focus on yeast, but in follow-up seminars I will also discuss bacteria and some yeast derivatives, so fermentation aids or functional products. But that's for later in this webinar cycle. So let's talk about yeast. Just a short introduction. Yeast is a sexual organism, and I have a slide on that today. It belongs to the fungus clade. If you look in the phylogeny, and if you check nature, there are around 200,000 species around. It's an estimate. I think there will be more, because we didn't sample, the whole world. If you look industrially, only a very small portion of this natural diversity is actually used. So in brewing, you have a few hundred strains available on the market in total, so including the wine, cider, ethanol, but also things like kombucha or meat or any other drink. You have around 1,000 strains that are available on the market. So not that much if you compare it to the amount of strains that are present in nature. At Le Saffre, we have around 8,000 strains in our yeast bank, and currently for the brewing, we only have a few. we only have a few available on the market, 3 lagers and 14 ale yeasts. So just a little bit. So what do all the yeasts have in common? It's these pathways actually. So the first, it's a little bit of a complex picture, but if you have the situation where yeast has oxygen available, it uses the so-called electron transport chain or oxidative phosphorylation actually to generate energy, and this is shown here in this slide. So what basically happens is a glucose is consumed, and then via this network of enzymes, it generates 28 ATP, and ATP is an energy carrier molecule. It basically provides the cell from energy. So per glucose, the generation is around 28. So 1 mole of glucose delivers 28 ATP. That's why in the situation where you have oxygen, the yeast is growing very fast. A lot faster than in the situation where you have no oxygen present, and that's shown here. So without oxygen, yeast uses the so-called ethanol pathway, and this is a very simplified representation of this pathway. So you consume 1 glucose and you produce 2 CO2 molecules and 2 ethanols. In humans, this also happens. So if you work out and your muscles get sour, it's because of this pathway. It's called the lactate pathway. So this also happens in bacteria, like in the Lactobacillus plantarum that we have in our range. In this case, the glucose is converted to lactates, and this lactate, it's an acid. It makes your muscles sour. But this doesn't happen in yeast, of course. This one happens in yeast, and as you can see, in the yeast pathway, only 2 ATPs are generated per consumption of 1 mole of glucose, which obviously causes the yeast to grow a lot slower. And that's good for us, because as brewers, we want the glucose to be converted into as much ethanol as possible and not that much into biomass. In total, if you are fermenting, around 5% of your sugar that you add goes into the biomass. So you lose around 5% of your fermentable sugars to biomass. So in brewing, you have 2 classic brewing yeast actually. The Saccharomyces pastorianus, which is the bottom fermenting cold tolerant yeast, to produce pilsners, lagers. And you have top fermenting yeasts, which are normally a bit warmer, and these are the Saccharomyces cerevisiae. That's to produce all your ales. So if you look at these 2 species a bit more carefully, obviously you all know the ale yeast. They have been around for hundreds of years already, and even thousands of years, because this was the start of all brewing, many years ago. Saccharomyces pastorianus came a lot later. It's unclear when it actually originated. It can be 100 years ago, it can be 150 years ago. But what happened is, only now 9 years ago, in 2011, a guy called Lipkind went to Patagonia just to sample nature actually for new species, and he found this species, Saccharomyces eubayanus. And when he was checking its genome, he found out that a large portion of the genome was very comparable to the Saccharomyces pastorianus. And in his study, he actually showed that the Saccharomyces pastorianus is a hybrid yeast. It's a cross, so a sexual cross between Saccharomyces cerevisiae and Saccharomyces eubayanus. So why am I telling you this? It's just because to show you that this is the pastorianus, or the lager yeast, is quite an exceptional special yeast. To give that a little bit more power, I'm showing you 3 other hybrids from nature. So for instance, peppermint. I think you all know peppermint. You can put it in your tea. It's actually also a hybrid between watermint and spearmint. And watermint and spearmint are not as strong actually as peppermint. So now the world is dominated by peppermint, and watermint and spearmint almost disappeared because this is a very strong hybrid. You also find different ones in the animal kingdom, like for instance the liger. A liger is a cross between a lion and a tiger. You can find them in zoos. I heard this picture is from a zoo in Germany somewhere. So it's quite interesting. This normally doesn't happen in nature. It only happens in a zoo. And these hybrids obviously cannot sexually reproduce anymore. Another example is the wolfin, which is a cross between a false killer whale and a dolphin. So it shows you how special hybrids actually are. And in Fermentis, we also use this technology in our research and development to actually produce new types of yeasts just by making hybrids. So in total, we have, as I already mentioned, 14 yeasts now on the market, 3 lagers and 11 ale yeasts. I will talk, like next week, I will talk about the BE256 and the W3470. What happens if you put these in different conditions? What happens to the flavor profile of the beer? I will also discuss in a later seminar LA01. This one is used to produce low alcohol beer. I will talk about Cef Sour LP652, which is a bacteria to produce kettle sour beers. I will also talk about Spring Blanche later on in one of the follow-up seminars. Repetition from last week, but it's important to my knowledge, to my opinion. If you look at simple yeast metabolism, what happens is you start from your malt, you do your mashing to create fermentable sugars. Normally, this is an average composition of a typical wort, so you have around 10 to 15% glucose. The majority is maltose, 50 to 60%. You have some maltotriose, 10 to 20%, and obviously dextrins, 15 to 20%. And depending on your exact mash scheme, of course, this can vary. What you next do is you ferment these sugars into main components that you always find in every fermentation. So you produce ethanol and CO2, as I already explained. You also produce a little bit of glycerol. You produce acids because your pH is going down during fermentation. You produce also a little bit of biomass, and you produce a lot of aromas and flavors. In the end, you also, depending on the yeast strains, end up with some residual sugars. These are most of the time dextrins and maltotriose or tetraoses, so the longer chain sugars. If you focus on just simply the aromas, which is important because the aromas actually and the aroma profiles make the differences between the yeast. So sometimes you have, if you have a yeast that is quite neutral, it will not produce all the flavors. If you have a very yeast that has a very strong aroma profile, it produces a lot. Well, it's a bit complex picture, but it's quite similar as the one I showed before. So you start with the sugar, it's consumed by the cell, and then you make ethanol as the main component, and CO2 of course. But as you can see, there are all kinds of other pathways leading to a lot of desired flavors, like the acetate esters, isoamyl acetate, and ethyl acetate are the two most important ones in every beer, because every yeast produces these two compounds, all Saccharomyces cerevisiae, and depending on the amount, you get more like a yeast that can be very suitable for a triple, for instance, or for a Belgian style blonde. If these are lower, you can produce, for instance, more beer styles like lagers or British ales. So these compounds are very important. Obviously, you make others, like 4-VG, for vinyl guaiacol, which is the spicy clovey note. This is only produced by yeasts that are so-called POF positive yeasts. It can be very dominant, but it can also very pleasant. So if you have a typical blonde style, Belgian blonde style beer, there always should be a little bit of this compound in the beer. So it's strong, but it's very pleasant. In some beers, this is not allowed. So, for instance, in lagers, you never want this compound in your beer. Some off flavors are also produced. Diacetyl, I think, so the popcorn, buttery flavor. Normally, you don't want that in your beer, but it's easy to get rid of if you use a diacetyl rest. So put the beer at some higher temperature for a day or two, you remove it because it can be taken up in the cell again. Sulfur is also a compound that is normally not wanted, not desired in your body. So this is a bit harder to get rid of if you have it in fermentation, but it's still manageable because especially the SO2 can be taken up back by the cell. So as I explained also last week, we came up with this tips and tricks book where you find a lot of information about yeast, about how fruity they are. I'll not go into detail. You can just simply go to our website, download this brochure. It has a lot of information. Also, the information that is relevant for today's webinar, which is actually the rehydration versus the direct pitching part. So, how do you use your active dry yeast in the brewery? As you all know, you start with water and malt. You do your mashing, you end up in the boil where you add your hops, and finally, after filtration, you end up in your fermentation tank. There you pitch the yeast, and sometimes you dry hop. I will not go into that today. So for lager yeast, normally your target is to start to have around 8 million cells per milliliter, which comes down to a pitching rate of between 80 to 120 grams per hectoliter. For ale yeasts, the pitching rate is around 50 to 80 grams per hectoliter. These values, these pitching rates, so dosing rates of the yeast, are actually rates that always work. And as you will see next, also these pitching rates, but I'll show you that next week. So these are just recommendations that we know will always work. So what's the difference between rehydration or direct pitching of yeast? So traditionally, what everybody, including fermenters, always said is you have to rehydrate your dry yeast before you pitch it in the fermenter. So what you normally do is you start with water, where you add the lager or the ale yeast at a specific temperature. You stir it just gently for a little bit. You leave it standing for a while, and then you pitch your fermenter. So this process, also in this presentation, I call rehydration. Depending on the temperature, you can vary this, so to give you a little bit more flexibility as a brewer. So if you put this at low temperature, so say for instance at 4 degrees, you have to pitch within 18 hours. If it's at 20 degrees, you have to pitch within 6 hours. If it's at higher temperature, like 25 degrees, you have to pitch within 4 hours. And this is all things we actually research. So these values don't come out of nowhere. So just say, to simplify things, normally you put it at room temperature, so around 20 degrees, and you wait for at least 30 minutes. That was always our recommendation. And then you pitch your fermenter. The direct pitching is something different. So you make your wort, and you fill your tank with, say, 1/3 of the volume. You add the dry yeast directly in the tank, and then you top it up with the rest of the wort, so the yeast mixes in a little bit. So that's what I call in this presentation direct pitching. So we got a lot of questions from brewers asking. So, I always pitch directly. I don't see any differences. So what's the impact? Why do you need to rehydrate? So this is already like 2 or even 3 years ago when we started to study. Okay, so what's the impact of the rehydration, and do we need to rehydrate actually? So the first thing that we looked at is the impact of rehydration on the yeast cell viability. So what's viability? Viability basically says something about the percentage of living yeast cells in your fermentation. So it's basically the difference between being alive or dead. And that's a bit visualized in this picture. So if you have a viability of 100%, all your cells are alive. And if you have a viability of 0, obviously 0%, all your cells are dead. Normally, viability should be between 60 to 100%. So what we did in the study, and I will only show, we did it for all the strains, but I will only show a limited number of results because, as you will see, they are all the same. So just quickly to explain the experimental background. So I'm showing today 3 ale yeasts and 3 lagers. And what we did is we rehydrated it 15, 25, 35, and 45 minutes in 10 times the volume. So that's of the weight that you add with the yeast. This is our normal procedure. Then we did no agitation. So we just added the water to the yeast and let it stand. We did moderate agitation, where we just simply swirled it for around 15 minutes at 100 RPM. And then we did vigorous agitation, which basically comes down to shaking the flask very vigorously. We did this at different temperatures, so 8, 12, 16, 20, 32, and 40 degrees. And we use different type of media. So we use distilled water, mineral water, tap water. We did it in 7% ethanol solution, so to mimic beer. We did it at wort at 7 Plato, 15 Plato, and 25 Plato. So why did we use mineral water, for instance? It is not something that you normally use. This is because we got this back from the market. Some guys were going to the supermarket, bought mineral water, and always used that to rehydrate their yeast. Actually, it's not the best way because some of you might not notice, but mineral water is not absolutely free of bacteria or other contaminants. I mean, the quality is normally good, but you should always start with something that has been boiled, just for you to know. So the results, first look at the viability of the ales. In these 3 graphs, you see on the y-axis viability versus temperature. So let's start with the T58. So the blue bars represent no agitation, just let it stand on the desk for a while. The reddish bars show moderate agitation, and the green bars vigorous agitation. And as you can see, at these different temperatures, so just without agitation, so the blue bars, you see that the results are very comparable. So in all this temperature range, the viability is very high. Also in the case of moderate agitation, it's very similar. You see it's a bit lower at low temperature compared to the higher temperature, but that's kind of logical because this is an ale yeast. It likes the higher temperature. If you look at vigorous agitation, you see the viability is going down. So we go below, say, around 80% at the lower temperatures. At the higher temperatures, the differences are not that big. Again, this is because ale yeasts like the higher temperature. For USO5, we see very similar results. So it works best without agitation or moderate agitation. For S33, it's a bit boring, but again, it's the same results or very comparable results. We have the highest viability in the conditions without agitation and at somewhat higher temperature. Logical because it's an ale yeast. If we look at the lagers, so I'm showing here S23 and S189. Again, at the different temperatures, you see that the viability in all conditions is very good. In this case, the lower temperatures actually perform a little bit better, which is logical because this is a lager yeast. It likes colder temperatures. And the results are exactly the same for S23 and S189 in this case, also for W3470 actually. So the three lagers that we have in the range. The best conditions seem to be without agitation or moderate agitation because the differences are not that big. In some cases, you see that the results are exactly the same. So then we looked at the rehydration time on the viability, both for lagers and ales. In this case, on the y-axis, we have viability. On the x-axis, we have the rehydration time. And we show in the different colors, we show different yeasts. So the blue one is T58, the red one is USO5, the gray one is S33. So if you look, for instance, at T58, you see already after 15 minutes of rehydration, you reach a very high viability, which means that, the recommendation that we normally did, say 30 minutes, is already long enough, is more than long enough. Rehydrated after 15 minutes. So you have to look in these graphs in this direction. For the USO5, very similar. There are no differences in rehydration time on the viability. S33 also. So no matter how long you rehydrate, you always reach the same viability level. For lagers, it is actually exactly the same. So in this case, 15, 25, 35, 45 minutes. For S23, you see this one going a little bit higher, so a little bit longer rehydration time. But if you look at the errors, it's all the same. It's very comparable. So in short, it's already complete after 15 minutes. So it's a fast process, rehydration. So then we looked also at the medium, so the wort or water. In this case, I'm showing the viability versus the type of water used for rehydration. So the blue bar, distilled water, red mineral water, and the green is boiled tap water. So as you can see, there are no differences in viability of the rehydration for, in this case, T58, S23, and USO5. So it's all the same. Then we also did the same in wort, and we did these at moderate agitation. The reason why it was done at moderate agitation is because all the experiments were done in one big research project, and when we started, we didn't know what the best condition would be, because you could also, if you look at the previous results, you could also argue it would be better to do it without agitation, but we didn't know when we started this. So again, viability versus different types of yeast. So for T58, for instance, the brown bar is water, the more light brownish bar is a wort of 7 Plato. The green, olive green, is 15 Plato wort, and the dark brown is 25 Plato wort. And you see the viability actually goes a little bit up when you rehydrate in a sugar solution, basically in wort. And this is the case for T58, S23, and USO5. So surprisingly, for us, you see that high gravity is actually beneficial for rehydration of the yeast, which also is already an indication that the direct pitch in your wort is actually beneficial for your yeast health. A similar, so this was done at 7 degrees. We have results also at 20 degrees, and you see a similar trend. So at somewhat higher original gravities, the viability of your yeast goes up. So conclusion on yeast cell viability, no or moderate agitation works best, as I showed. Temperature does not significantly impact the viability. So even with or without agitation. Type of media, so it doesn't matter if you use water or tap water, mineral water. It doesn't significantly influence the viability. What we saw, as I showed in the previous slide, is that if you increase the gravity, so if you add sugar, it actually is beneficial for your yeast. And there was no difference observed with different rehydration times. So it was done at 15 minutes. And the conclusions are the same for ales and lager yeast, which is very nice. So we know now that no matter what you do, the viability of your yeast is not impacted if you pitch directly or if you rehydrate in all these different conditions. But what does it mean if you look at the cell vitality? And to explain cell vitality, I have these two pictures. So you have here the Bundys. I don't know if you had this television show in Estonia, but this is a family which is kind of lazy. So they are sitting in the couch. They are all alive, even the dog. So the viability is 100%. But obviously they are not as vital as these guys who are running the marathon in New York. So these guys are more vital. So they have a higher energy state than these guys. So the conditions that we tested, again, I'll show 3 ale yeast and 3 lager yeast, SO4, USO5, T58, and S23, S189, and W3470. The rehydration conditions we did is no rehydration, so we just did a direct pitch, which is always called. We did a rehydration in water with moderate agitation, which we call the W, and rehydration in wort with moderate agitation in 15 Plato wort. We used 50 gram per hectoliter pitching for the ales at 15 Plato and 20 degrees. And for the lagers, we used a pitching of 100 gram per hectoliter if we did in wort, again, 15 Plato at 14 degrees. So these were the conditions. So first, and then we did obviously check the vitality, but we also did it for aged yeast. So as I explained last week, you can age yeast in a forcing test to mimic the shelf life of the yeast. So this yeast, all the yeast that we tested were aged for 3 years to make sure of fresh yeast versus aged yeast can be studied. I will just read it. The influence of increasing agitation Reducing viability is optimally. What kind of agitation process are we talking about when we say moderate agitation or vigorous agitation? How can this agitation reducing viability be explained? Doesn't agitation bring oxygen and aeration, good mixing, meaning hydration? Is there a level of intensity? The reason I asked, because adding yeast after fermentation tank is filled seems not as good for fermentation quality versus adding yeast in the beginning of filling the fermentation tank. So there's a lot of questions in one question. In terms of agitation, so moderate agitation, what we did actually is you have a pot, you add the yeast, you add the liquid, and then you stir it just gently with a glass stick, basically, and then you let it stand, and then after a while you stir it again. If you do vigorous agitation, is what we did is we put it in a jar with a lid on, and then we were shaking it like this. So the reason why force is not good for or not beneficial for yeast is if you put a lot of force on the cells. I mean, these cells are dried, so they're 95% dry, so there's almost no water, and the cell membrane is a little bit wrinkled. It's not a smooth surface, as I showed last week. So if you add a lot of force to these very fragile cells, they will break. Simple as that. And that's why, and that's also shown in the results I just explained, is that if you do nothing, you basically give the yeast more time to get the liquid into the cell and restore the membrane structure. Oxygen level, also something that you asked, doesn't agitation bring more oxygen? In our case, if you have a dry yeast, you don't need to oxygenate your wort. So all oxygen is only required in metabolism of the yeast to produce sterols and polyunsaturated fatty acids. But in a pack of dry yeast, all these compounds are already there. So you don't need to aerate the wort. If you always have been doing that, if you're happy with it, you can always do it. But normally you don't add oxygen when you already added the yeast. So normally you oxygenate your wort if you prefer that. And then after that you add the yeast, not during. Because if you do, then you're not making any beer, you're making biomass. So you're producing actually yeast because it's just consuming oxygen. And as I explained in one of the early slides, you generate a lot of energy and you just put it all into biomass. There's no need to produce ethanol. Does that answer your question, Thomas? Okay, so let's continue. What we did in an analysis, obviously, everything was done in triplicate. We did the kinetics, which is very valuable for us because it says a lot about how your fermentation is going. And we did it by just measuring the weight loss of the bottle. As I showed in one of the early slides, there's a direct correlation between the amount of CO2 that is produced and the amount of ethanol. It's a 1-to-1 molecular ratio. So if you measure the amount of CO2 that escapes, you also know how much ethanol is produced. And at the end of all fermentation, we looked at the final ethanol production and also some volatile compounds to say if the aroma profile will change in all these conditions. And we looked at acetaldehyde, esters, higher alcohols, and vicinal decatones, so typical beer flavor compounds. So let's start. First the results of S33, and I have quite some graphs here. So I'll start with this one. where we show actually the kinetics of the fermentation as the amount of ethanol that is produced over time. The blue line is the situation of direct pitching. The orange line is the situation if you rehydrate in water. And the gray line is the situation where you rehydrate in 15 Plato words. And as you can see, the kinetics, the lines are actually completely the same. So there's no difference in fermentation kinetics for the three situations. If you look at final ethanol produced, we see there's no difference in the three situations. So they all end up at around 5.4% of ethanol. If you look at the volatile compounds of the final beer, so this beer, you have to compare it in color. So the blue bars represent the VDKs, the orange, the higher alcohols, the gray ones, the esters, and the yellow one, the acetaldehyde. As you can see, for instance, for the VDKs, in direct pitch, rehydrate in water or rehydrate in 15 Plato wort, there's no difference in aroma profile. Similar for the higher alcohols, similar for the esters. So that was quite interesting. We didn't see any difference in the flavor profile of the beer, no matter how we started the fermentation. If you look at the apparent degree of fermentation, we see it's also very similar. So in this case, it's S33. The apparent degree of fermentation is quite low with this yeast because it doesn't consume any of the higher sugars and also not that much maltodextrose. But you see that it's very similar in all the three conditions tested. T58, again, fermentation kinetics, as you can see, there's almost no difference, no matter how you do it. Final ethanol concentration, we see this looks a little bit lower if you rehydrate in water, but actually if you look at the error bars, they're all very comparable. So there's not a significant difference between the situations. If you look at flavor profile, again, I'm sorry guys, it's a little bit boring, but we didn't find any difference between direct pitch, rehydration in water, or rehydration in wort. Also for the apparent degree of fermentation. US05, a strain that's been used a lot by you guys. Also here, no difference. I can go quite quickly. You can see fermentation kinetics are the same. Final reached alcohol is the same. Aroma profile is the same. And the apparent degree of fermentation is the same. So this is quite nice. Then I'm showing you here what's the difference between fresh US05 and aged US05. Just showing the fermentation kinetics here. So for the fresh yeast, it's you see there's almost no difference between direct pitch rehydration in water and rehydration in 15 Plato wort. I mean, the difference that you see here is normal biological variation. It's exactly the same, and the beer ends up at the same alcohol concentration in the same time. So there's almost no difference. If you look at aged yeast, so this has been aged for 3 years, the pack, and again pitched directly in water and 15 Plato wort. You see here also there's no difference in fermentation kinetics. So what about the lagers? Lagers are a little bit more fragile than ales. I'm showing here W3470, direct pitch, rehydrated in water and rehydrated in wort with the same color coding. If you look at kinetics, obviously the lagers are a bit slower. You see they're exactly the same. So there's no difference in fermentation kinetics if you compare to how you start your fermentation. Final ethanol concentration also here, no difference. If you look at the aromatic profile of the main components, you also see here no difference in VDKs, no difference in higher alcohols, no difference in esters, no difference in acetaldehyde produced. And also the apparent degree of fermentation was the same in all three conditions. For S23, I can be quite quick on this. No difference. For all the three conditions, we find very similar results. So no significant difference in the final results. Then again, fresh versus aged for 3 years. If you look here at the kinetics, you see obviously in the normal biological variability of the three conditions, but it's very comparable. It's very similar. For the aged yeast, indeed, again the same. So these two profiles are exactly the same. There's no significant difference between fresh or aged yeast. So if you have a pack of yeast that it has been in the refrigerator for 3 years, you will get exactly the same result if you compare it to a pack of yeast that's very fresh. So the conclusions on yeast cell vitality: no significant differences between the direct pitch, rehydration in water, and rehydration in wort. We saw similar fermentation kinetics. We saw that aged versus fresh is also the same in kinetics. And we also saw that the production of volatiles and the final ABV and final apparent attenuation is the same. So, in summary, direct pitching in wort or rehydration under a wide range of conditions can be used for all Fermentis easy-to-use yeast strains. And easy to use, I think a lot of you guys have seen this on a pack of yeast. If you have this brand, because it's a brand by Fermentis, it means that this study I showed today has been done with this particular yeast. So you can choose, if you prefer to rehydrate or if you like to do a direct pitch. The choice is yours. The result will be the same. So this is a brand that if you have it on the pack, it's up to you what you prefer doing. And then I see some questions coming in, but I'll just finalize first. I want to point out again the Fermentis app, because all this kind of information is also present in the app. You can download it for free. There's a lot of information. As I already mentioned, next week we'll talk about the impact of temperature, pitching rate, and original gravity on the flavor profile of beer. And to make you a little bit enthusiastic about this, I will also show you that you can brew a lager beer at high temperature without compromising the flavor, which means that you can brew a lager beer in at least half of the time, which means you can increase the productivity of your brewery if you do it at higher temperature. But that's something for next week. Last but not least, I really would like to ask you to complete this short 2-minute questionnaire, just to get more insight in your needs, and also if you have specific subjects you want me to do a seminar on. And I can quickly copy this form, the link to the form also in the chat. So you can click on that if you cannot do it via the phone. And with this, the presentation is done. I'll just go into to questions. So a follow-up question first from Thomas. When we say rehydrated in 15 Plato is not a direct pitch in full wort volume, no, it's not. It's 10 times the volume. So if you have 10 kilos of yeast, you rehydrate in 100 liters of wort. So it's not a direct pitch. It's very comparable, obviously, but we did it in a separate vessel and did the rehydration. We waited for the normal 30 minutes and then pitched the big fermenter. Rehydration. So I think what gravity is the word in this study. The results, the last results I showed were all done in 15 Plato wort, but we did them at in different words. So 7, 12, 15, and 20 Plato. Where can we find slides or recorded presentations? Alar will send you the link to this webinar because it's recorded.
Yes, I will put the link to the Facebook event discussion, so you can find it there.
Perfect. Then we have a question from Anne. You have compared effect of temperature and media. Have you compared different levels of oxygen? No, we didn't actually. What we found is, and I already touched this briefly, is if you use dry yeast, you don't need to aerate the wort. That said, a lot of brewers and also maltsters actually say you always have to aerate the wort. Fermentation-wise, it's not needed. And me as a biotechnologist with a lot of experience on fermentation, is I always see it like this. So if you have a yeast, in a pack that you want to ferment to produce beer, what you do if you aerate the wort is you no matter how you do it, if you rehydrate or direct pitch, you put it in your fermenter, and when there's oxygen there, the yeast will rehydrate and start by producing all the aerobic pathways it needs in this condition, because in the condition there is oxygen, and it will completely focus on producing biomass. Then maybe after half an hour or after an hour, the yeast discovers there's no oxygen anymore because all the oxygen has been consumed. Then it has to switch to anaerobic metabolism. So it has to build up the complete battery of anaerobic pathways that you need to do anaerobic metabolism. And then it will start fermenting. In my opinion, it's better to start in the condition where you want your yeast to perform the best. So if you don't want to shock the yeast or shock is a big word, but what happens if you start in an anaerobic condition, so without oxygen, you put in the yeast, it rehydrates, there's no oxygen, so it will immediately produce all the metabolic pathways that you need, so the enzymes for the metabolic pathways that you need for anaerobic metabolism. That said, it's a bit complex if I look in the wine, because we did studies with oxygen in wine, so it's a bit different, the fermentation, because you start on a must, so mainly primary sugars. What we saw there is that if you aerate the wort, sometimes, so not always, but sometimes your final gravity ends up a little bit lower. And then in the case where you don't aerate the wort. So and that's obviously also depending on the yeast strain. So it's not that we are completely against aerating of the wort. What we do know is that it's not required, because all the compounds that you need, and in this case it's specifically sterols and polyunsaturated fatty acids, are already in the pack. So you don't need to aerate the wort. just to explain where the whole word aeration comes from, back in the days when there was no dry yeast, everybody was working with liquid yeast, obviously. And everybody was propagating themselves. So they would crop the yeast, sometimes do a propagation, sometimes not, and then they would repitch it for the next fermentation. If you do that in anaerobic conditions all the time, you will see that the performance of your fermentation will go down quite rapidly, because a yeast, and this is valid for all the yeasts out there, yeast cannot produce sterols and polyunsaturated fatty acids if there's no oxygen. So at some point, the brewers found out that if you aerate your wort, you restore actually the viability and the performance, because you allow the yeast actually to produce these required compounds, sterols and polyunsaturated fatty acids. But as mentioned, in the pack of dry yeast, all these compounds are in there. It's basically in the percentage of dead cells. So if you have a pack of yeast, you have around 95% viability. So all the compounds that you need, like sterols and polyunsaturated fatty acids, are already in the portion of the dead yeast cells. So you actually give them some nutrients by also dosing a small part of dead cells. Does that answer your question? Okay, I think so. Now we have a new question from Thomas. I was told by Lallemand that you don't need to oxygenate wort for dry yeast, but reproduction cell multiplication will be limited from not having oxygen. Yes, that's correct. If that is true, wouldn't a lack of oxygen then limit fermentation efficiency, speed, quality? I'm changing a bit the topic, but did I understand correctly that S33 is a bread yeast? No, S33 is a beer yeast. So I'll answer this question first. But if you look, and maybe I will show it also next week to clarify this. If you look and make a phylogenetic tree of all the yeasts out there, so this has been done in many academic studies, but we as fermenters also did that for our yeast, then you can classify yeast based on the original origin of the yeast. And the original origin of the yeast comes from the academic study. So there is one, or actually two big academic studies, one done by Verstrepen in Leuven and in Belgium, and one done by Brian Gibson, who's in Finland, who basically sampled a lot of yeast strains and looked genetically how different the yeast strains were. And then based on that, you can build a kind of a tree of life. We call it the phylogenetic tree because it's only one kingdom, only yeast. And then the distance between the yeasts in this phylogenetic tree says something about how genetic related they are. Since they know where the origin of the yeast was, so they used yeast from wine, they used yeast from they typically used for pizza, for instance. They knew already the origin, and then if you look genetically, they found out how related all these yeasts were. And in their research, they said, okay, so these are typical, genetically, these are yeasts that have been typically found in. They also had two clades. One of them was typically found in German-style beers, and one was typically found in ale-style beers. So I will try to include that in next presentation to explain it more careful. But the bottom line was that they actually introduced this origin of yeast. And then when we did our study which we did with Brian Gibson and looked at the genetic relatedness of our yeast that we have on the market, and then if we compared it to these studies, then indeed S33 clustered in the clade of bread yeast, but it's just genetically. It doesn't say that it is a bread yeast. And to be honest, you can use S33 also for bread. I did it already. If I bake a bread, I use because I have all the beer yeast in my refrigerator, obviously, and you can easily use them for bread making also. In the end, originally, all industrial yeasts, if you go back many years, actually originate from bread in some way, because back in the days when people were producing bread, the whole fermentation was discovered many thousands of years ago already by the Chinese or Egyptians. They noticed that if they were making bread and let it stand for a while, it started fermenting, so they got alcohol out of it, and that's how the whole beverage making in the end got started. So a lot of beer brewing strains, if you bring it bottom line, comes in the end, they all come from bread in some way. So I hope that answers your question. And Anne is not completely satisfied with what I explained about different levels of oxygen. Yes, we did not test it. So, but what we know, as I explained, is that if you have the condition where there is oxygen, you only have this condition that you only need this condition to produce sterols and polyunsaturated fatty acids. This is not theory. This is actually metabolically a metabolic requirement by the yeast. Maybe in future studies we will carefully look at the impact of oxygenated wort on final gravity, on flavor profile, etc. But so far we have not been doing that, and the reason is mainly because brewers all do different things. So as I showed in a previous webinar, we can only do basic things, like we have a standard wort. Most of the times it's a simple Pilsner wort with a Weiermann malt, originated from 2-row barley, and most of the times it's spring barley. And we don't vary that much. We don't add hops. We always add alpha acid to make sure there's no impact of the hops in all these baseline studies. Just to give you an idea, it's undoable to test all conditions that you guys are doing, because you make many different types of worts. Some of you aerate, some of you don't. You do it at specific temperatures, so it's practically it's unfeasible to test all the conditions. So we test what we think is relevant and for you brewers, and that's the information we share. And then if you do things differently and want feedback, if you share the results, we will look at it and come with decent feedback for your specific condition, because it's undoable to come up with a general explanation for all the conditions. Then Timion asked a question: is direct pitching acceptable regardless of original gravity? At very high original gravity, I feel a little concern over osmotic pressure. I share your concern, but as I showed in this presentation, we didn't see any difference up to 20 Plato, which is already quite a high gravity. Actually, we saw improvement at high gravity of kinetics, or it was not statistically, it was a trend. So we saw that actually the higher the gravity, the better it is for rehydration of the wort. Why that is, we don't know. It's just something that we observed. So up until 20 Platos, don't feel any concern. It's you can do it. Then I have one question from Mihail. I hope I pronounce it correctly. Would you agree with the statement that aeration would be desirable in the case you don't have enough cells to begin with, like when you are underpitching intentionally or not? If you don't have enough cells to start with and you want to produce more cells, obviously you have to aerate, because that's the only way to produce biomass. If you intend to do an underpitch, make sure you underpitch. Otherwise, you're not looking for that. And I will show you actually in the next webinar. I will show you the impact of underpitching of both ale and lager, and what that does to your beer, to your final gravity, and to your aroma profile of the beer. So join next week, and I can show you a little bit more about that. Then Timion, I'm doing a few beers with 36 Plato original gravity. Well, I'm not sure about this. 36 Plato is extremely high. So we didn't do that. So I cannot say, okay, you can pitch directly or not. What I would suggest is just do a small experiment. So take out some of this 36 Plato wort, put it in a small jar, add some yeast, and see if it starts fermenting in the normal time. How do you filter 36 Plato? Maybe you add a lot of sugar. Then we have one question of Radoslav. What method of direct pitching do you recommend when the fermenter is half full, or sprinkle at the end? What we recommend is, if it's possible in your system, to only fill the cone of the fermenter if you have the conical tank, so say about 1/3 of the volume, then add the yeast, and then add the rest of the wort. Because in that case, you mix in already the yeast. It's possible to sprinkle it on top, but what we hear from the people on the market, from you as brewers, is if you have a high dosing, sometimes you end up with with a small pile of yeast sitting on the top, and it takes some time to sink in the wort. So we recommend 1/3 of wort volume, pitch the yeast, and then add the rest of the wort. Timion gets this high Plato by adding maltodextrin and invert syrup. Okay, that's the way to do it. But did you ever, Timion, pitch directly in this situation, the yeast? And then we have Thomas commenting, boiling BG is another technique. I'm not sure what that means. Boiling. Oh yeah, boil off. Yes, some brewers indeed do 24 to 36 hours of boil. Yes, I know, but it's very unsustainable to boil that long. And also, if you boil, if you start from barley, you add sugars or syrup, it doesn't really matter, but you end up with a very high gravity wort. If you start boiling it for a very long time, what you actually do is you induce a lot of the so-called Maillard reactions, which are chemical reactions between amino acids and sugars, and this actually darkens your wort tremendously. So you can only do that for certain beer style. It's comparable if you if you cook a steak, it becomes brown, and this brown coloration is actually a result of Maillard reactions. And you do exactly the same if you boil for a long time the wort. You actually make it darker and darker. So in some situations, if you prefer that, you can do it. But I brew myself quite a lot, and I always prefer to boil as short as possible to get at least some control on the color of the beer. If it's a dark beer, I prefer to use dark malts instead of boiling long to get a darker color. But it's all up to you what you want to do. So I think those were all the questions. If you don't have any questions anymore, I'd like to thank you for your presence, and I hope to see you next week again at 9 for the next very interesting webinar. I promise it's going to be more interesting than this one.
Okay, thank you, Gino.
Okay, I will share this recording with Allard, and he can share it to Facebook.
Yes.
Okay. See you next week, guys.
Thank you. Bye.
Bye.